Things get a little more difficult when we get into artificial. In an artificial transmutation reaction, we have to hit the nucleus with another particle. So we're going to bombard, I think that's the word they use the most, bombard the nucleus to make it unstable. So for an artificial reaction, you're going to see an element and you're going to see some particle that we've managed to accelerate at that. What you're going to find most of the time is those particles that they're accelerating at it are going to have a charge, because we use a charged field to accelerate those particles. That's not to say that they couldn't maybe direct other particles at a nucleus, but to really accelerate it, it would have to be a charged particle like this one. So this one, I would have to give you one more piece of information if you were to figure this out on your own, because I couldn't leave 2 bits missing in this case. None of these are going to be in your table N, so you won't be able to figure out the decay mode. I would have to tell you maybe the particle emitted, which in this case we're going to say is a hydrogen nucleus, and then you can then figure out what the element is. Or maybe I give you the element and you would have to figure out the particle. In this case, I gave you the particle that's emitted. Now on this side, our total mass would have to be both of these, so it's going to total 18. Since this already has a mass of 1, this needs to have a mass of 17. Now this side totals 18, so does this side. A little more complicated math this time. And then the charge, or the atomic number, needs to total 9. We already have 1 here, so this will be 8. And you just look in the periodic table again, you're going to find that that's oxygen, so we're going to use symbol O. Right? There are 2 types of artificial radiation. One is fission, so that's the one we'll talk about first. In fission, we're actually going to be splitting atoms. This is the nuclear reaction that happens in a nuclear reactor and also in a nuclear or atomic bomb. Not in an H-bomb, though. You need to know that what happens is it is artificial, so we're going to accelerate something at the atom, which will then split into different isotopes. In fact, in this case, we're going to call this uranium-235 atom, and this is actually a neutron directed, not accelerated, at the atom. And when it decays, it actually spits out krypton 91 and barium 142. And in the process, it also releases additional neutrons, which then can hit other uranium atoms, which will then split into krypton and barium and so on. There are some things that are produced in this reaction that we don't really understand, so they try to control it as best they can. There are only 3 isotopes that can be split, and they are uranium-233, uranium-235, and plutonium-239. You need to memorize those isotopes. Those are the only ones that we can use in a fusion reaction. All right, controlled fission versus uncontrolled fission. Uncontrolled fission is what happens in a nuclear bomb. There's nothing in there to control the reaction. Once it starts, there's no stopping it. It's completely unstoppable until it consumes everything that it can. Controlled fission is what happens in a nuclear reactor or a nuclear power plant. In a nuclear reactor, we use something called a control rod that helps to control what those neutrons are doing. This reaction is actually something that can get kind of out of control, and that's what happens in a meltdown, a nuclear meltdown, but it'll never be a bomb. It's not so uncontrolled that it could ever be a bomb. It just gets so hot, so very, very hot, that it'll actually melt the core. It'll never blow up. And that's actually what happened in Chernobyl and also in Japan after the tsunami. Those isotopes that we talked about, uranium-233, uranium-235, and plutonium-239, are actually not very common. They're hard to find. So we have this other type of nuclear reactor we call a breeder reactor, and it kind of makes its own fuel. If you give it uranium-238, which is much more abundant in the crust, it will actually use that uranium-238 and turn it into plutonium-239, which we can use in a regular reactor. It's also one of the three. So you may think to yourself, especially since you lived through the scare that happened in Japan, that nuclear power is scary and unsafe, and you would never, ever, ever consider using nuclear power. But let me tell you a couple of things so that you can make informed decisions. One of the amazing things about a nuclear power plant is that they produce huge amounts of heat. Way more than we could ever produce in other ways. To give you an idea of what that looks like, let's say I had 1 gram of TNT dynamite. If I exploded that 1 gram of TNT, I would get 2.8 kilojoules of energy, of heat energy. If I had, and we have a coal burning plant nearby, 1 gram of coal, and I burned it, it actually produces a little more than 10 times that. I know that may seem kind of crazy when TNT makes an explosion, but that's fast. If you've ever seen coal burn, it burns nice and slow and really hot. It actually produces per gram about 30 kilojoules of heat energy. So it's not bad. So for 1 gram, you're getting a lot out of that. But if I had 1 gram of uranium-235 and I used it in a nuclear reactor, I would get not 80, not 800, not 8,000, but 80,000 kilojoules of heat energy. So you can see per gram that a nuclear power plant produces a huge amount of heat. Might be scary to you, but it's really per gram the best way to produce heat, which then we use to boil water, which the steam would turn the turbine and create the electricity. Now, there of course are cons, and I'm sure you can come up with some of these. The fuel is not abundant. It's hard to find those 3 isotopes in the crust of the Earth. There are some unknown particles produced. We haven't quite figured out what all of them are or what happens as a result. There are some hazardous byproducts. There are some radioactive materials that are made. In fact, strontium-90 is one of the byproducts that we have to find a way to store. And unfortunately, strontium is really important in our bones, and it gets stored there for a lifetime. So if somehow it gets into our food supply, strontium-90 would be stored in our bones and continue to radiate yourself from the inside out. So not cool at all. And then, of course, the storage of the waste and the transport of that waste. People talk about how, oh, let's just dig out the center of a mountain and jam it in the middle of the mountain. Well, that sounds great. Nobody lives there. Who's it going to hurt? But you've got to get it there. So those are all things to keep in mind. So that's all dealing with fission reactions. Now I want to talk about the elusive fusion reaction. Fusion is where it's at, I'm telling you. Fusion is not the splitting of atoms, but the combination of those atoms. So we're going to try to combine some atoms. And in this reaction, you can see here's an example of it. We have a hydrogen atom and another hydrogen atom. And when we make them fuse, look what we get. Helium. Completely harmless helium is. It's awesome. And huge amounts of energy, even more than what we get from a fission reaction. It's pretty awesome stuff. The problem is that in order for this reaction to occur and you to be able to fuse those two atoms together, you need incredible amounts of heat. This reaction occurs on the sun. Should use the pen part. And also, we've made it happen on Earth, but the only way we can do that is by exploding a nuclear bomb. So we explode a nuclear bomb, which in turn makes fusion happen. When we do that, which hopefully we won't be doing anymore, that's an H bomb or a hydrogen bomb. That's why they call it a hydrogen bomb. Because you're actually using hydrogen and fusing it with more hydrogen, and you make helium. The hydrogen part of the bomb, really the scary part is the energy. You're releasing a huge amount of energy all at once, and we have no way of really capturing that energy because it's so fast and it's an explosion. Think about that TNT. It's so fast, how could you possibly collect that? So the same thing is true for this, except it would be even larger amounts of energy than a uranium-235 reaction. Really, really cool because the waste product is helium, no big deal. But the problem is when we have done it on Earth, we've had to explode a nuclear bomb, which is not cool. Not cool at all. It's devastating. So let's talk about some pros and cons then for fusion. It only produces helium. So it produces helium as a waste product. So you don't have to worry about nuclear waste. And if we could do it without exploding a nuclear bomb, that would be super awesome. The other thing is that it produces even huger, if that's a word, huge amounts of energy. All right. And then, of course, the cons. We currently don't know how to do it except to do it at an incredibly high temperature. Make that really obvious. Really, really high temperature. And because this happens at such a huge temperature, and then it happens so fast with so much heat energy, it's impossible to contain. If we could figure out how to do fusion at a cool temperature and contain the reaction to the point where we could actually use the heat produced, you would solve the world energy crisis. You're producing something that's waste product is helium. You're getting a huge amount of energy. but because of these cons, we can't currently do it. So let's hope in the future somebody figures out cold fusion. All right, the last thing we have to talk about, and all of this is stuff you have to memorize. These are often multiple choice questions on the exam, are uses for different radioisotopes. TC99, they use to scan for brain tumors. So sometimes they'll give people this radioisotope and then they'll scan their body to see where it goes. Iodine 131, they'll use for thyroid disorders because the thyroid actually uses iodine. So they can kind of calm it down sometimes by giving it iodine 131. Radium 226 and cobalt 60, it actually has two uses. Sometimes it's used for cancer therapy. It's used for radiation. When you hear about somebody getting radiation therapy, that's what they're using. And sometimes they use it to kill bacteria and yeast and insect eggs and things like that in food. So if you hear about food being irradiated, this is what they're using in order to do that. And then I'm sure you've heard before, carbon-14 is used to radioactively date different biological things. So things that were once living. It works really great because during your lifetime you're continually uptaking carbon-14 at a very regular rate, and as soon as you die you stop uptaking that carbon-14, so it begins to decay, and they can then figure out how much it started with, and then over the time how many half-lives have elapsed, and then of course the time that has elapsed. And then the last one you need to know is also for radioactively dating things, but this is for geologic time. So you can use uranium-238 for geological dating. So those are all things that you need to memorize for the quiz and also the exam to be coming shortly.